All right, so here's an example for class 20. And I want to flip my screen around. Should have done that before I started recording, but it is what it is. Flipping and flipping and flipping. Thank you. And no, I do not want to turn it into tablet mode. All right, so we have 1,000 pounds at the end of this support on this end of this bracket with 3 bolts, A, B, and C. And we want to determine the load, including the direction of the primary and secondary shears, and identify the bolt carrying the most shear load and determine its factor of safety against, I would say, shearing, but he says yielding, shear yield. Maybe that's what we'll say. So we can go ahead and get the F first. That's just going to be 1,000 divided by 3, or 333.3 pounds. And then, well, we want to get the centroid of this bolt pattern. So breaking this thing apart, we know that this could be 4 inches and 2 inches, and also 2 inches here and 4 inches here. So right there, just based on the fact that it's a triangle, is where the bolt pattern is going to be centered. And we would have radii that would look like this right here. So that's going to be, let's call this RB, and this would be RA, and then RC. And if we want to get those dimensions right here, we could say that RA is going to be equal to the square root of 2 squared plus 2 squared, right? Right here and right there. So that's going to be 2.828 inches. And then we'll notice that RC is going to be equal to RB. And that's going to be the square root of 4 squared plus 2 squared, or 4.472 inches. We might also want to get the angles in these, and I'm going to call this one theta B. It doesn't matter which one we call it right here, but I guess I decided in my notes to call it theta A right here. And then this one right here, we call that theta C. And so theta A by inspection is 45 degrees. Theta B is equal to theta C. And I decided to take the inverse tan of rise over run, and I'm going to say it goes up 2 and over 4, so that ends up being 26.57 degrees. I'm going to get the moment that's going to be caused by this. So where that's going to end up being is the distance right to there, right, from the force to the center of rotation of this thing ends up being the moment. So that's going to be 42 plus 2 plus 4, right, or 48 inches. So the moment, we don't have to do a free body diagram of this, is just going to be F times that distance. I guess I call this L in this case. So FL is just going to be 1,000 times 48. I can do that math in my head. 48,000 inch-pounds. And now if we want to get the secondary shear of A, that's going to be M times RA divided by RA squared plus RB squared plus RC squared. And that turns out to be 48,000 times our RA, 2.828, divided by 2.828 squared plus, and then since RC and RB are equal to each other, we only have to do this once, 4.472 squared. Oh, and by the way, if we want to net this bottom part right here, that's and they're going to be 48. That's what that ends up being, and this whole thing equals 2,828 pounds. F FAB double prime and FC double prime are equal to each other, and they're just MRB, whatever you care. Well, we just write the thing out right here. It's going to be 48,000 times now the 4.472 and divided by 48. Same thing on the denominator, and we end up with 4,472 pounds. All right, so if we were to draw this, and maybe it's good to put it over to the side over here, maybe draw these out. I don't want to use up too much room. Let me draw these out. What's going to happen with all these values is we're going to have F prime that way, F prime that way, and then maybe I'll find let's do orange right there. Oops. And we want to draw these so that they look perpendicular, because they are. And so that's that way right there. And then this is that way right there. And then this is that right there, right? So if you're going to look at this, we would come up here, and we're going to end up with this value right there, right? So if we do this parallelogram, end up with that value. This parallelogram, end up with that value, right? And so let's get these figures. We could tell already that B is going to be the worst one, but let's get all of them anyway. So if we start off with let's start off with A right here. So this is going to be FA up here. That FA is going to be equal to, oh no, let me go FAX. FA double prime X is let's see, I gotta draw the thing out here. It goes this way up here. That's a better place for it. And you know that this right here is going to be theta A right there. Even though it doesn't look like 45, it should look like 45. Maybe something more like that right there. That's so we end up with where did you go? 2,828 times the, and I guess the way I drew it up above, that's going to be the sine of 45, although it doesn't really matter, right? Because it's 45-degree angle. So that's going to be 2,000 pounds. And we could say by inspection that FA Y double prime is going to also be 2,000 pounds because it's a 45-degree angle up above. And because of that, we could just solve for FA, and we know the X direction is going to be 2,000 pounds squared plus the Y direction. Now taking a look at this, the Y direction is upwards, so it's 2,000 pounds, but the F prime, that's right here, that F prime is downwards at 333.3, and that's all squared. And so we end up with, I guess I'll keep going green, we end up with a answer of 2,604 pounds. All right, so that's what ends up being FA. Now let's continue on. Let's go to F. Let's go to FB, alphabetical order. FBX double prime is going to be the magnitude of this, or 4,472. And then I should draw it someplace where it's much neater. Maybe I'll draw it up here. And you can see that this angle right here is going to be the same as the theta B that we got up there. So in the X direction, it's going to be the sine of 26.57. Or we end up with, it ends up being 2,000 pounds. It's kind of convenient, or maybe it isn't convenient. And then FBY is just going to be the cosine, right? So 4,472 cosine of 26.57. And we end up, if we do that, we end up with, I think, 4,000 pounds. So if we go to fix this, if we go to get FB, I say fix it. If we're going to get the magnitude of FB, right, that's that corresponds to that green guy there. It's the square root, take the x squared, because the only one thing in the x direction. And then we take the y component, which is downwards, of the double prime, but we add, because the f prime, right, the f prime is downwards right here, so we add the 333.3 squared, and we're left with a force of 4,773 pounds right here. And continuing on here, if we wanted to get the FC, we end up finding we're going to get something similar to the, we actually get the same value as FA, but we don't know that just yet. We get 4,472, and looking back at this, see if I could do this correctly. I think, yeah, it comes up this way, and so right here is going to be the angle theta C. So we want to get to, that's going to be times the cosine. Do I have that right? Yes, the cosine of 26.57, and we get 4,000. And then we take the FCY, and obviously we just take the sine this time of the same angle. And that ends up being 2,000 pounds. So when we go to get FC, we have to be careful here. We take a look at the square root, and we get to take the x squared. So 4,000 squared plus, and now we take a look back, well, let's see, back over here. It's going to be the x squared, but it's going to have a vertical component. It's going to be positive of double prime, but the single prime is downwards, right? So in my notes I actually have that written wrong. So what we write for C is, I'm going to say 2,000 upwards minus 333.3 squared. And you know what? I don't trust that number right now. So let me just double check. 4,000 squared, and then I guess I might as well go 2,333.3 subtracted that squared, add them together, square root. Sure enough, you get 4,333. So I think I said something wrong in class. 4,333 pounds. Yeah, I did it wrong in class. You guys, you didn't catch me. Of course, you probably did. Nobody said anything because everybody likes to be quiet. So to get the angles on this, I decided to, what did I do? I guess I went one at a time. It's not 100% necessary to get the angles on it, but I did. So here is A, B, and C right here. So I just drew them out separately. I didn't have to do it this way. But we have F prime this way, and then we have F double prime at A, and so that's going to be up here. Let's see, did I do this right? Yep. I think it's going to be like that right there. All right, so we want to get this angle right here. I'm going to call this, what do I call this? I guess theta FA. That's a weird thing to call it. I didn't even write it in there very well. Theta FA. I said that theta FA is equal to the inverse tangent of, let's see, okay, the horizontal of this, right, if you recall from right up here, the horizontal of A is 2,000. All right, so that's run. The rise is going to be the vertical, the Y of FA, which was also 2,000, but it's going to be minus our 333.3. So that's going to be 39.8 degrees, and it's going to be pointing upwards. If we were to take the next guy here, and that's going to be B, and we'll see down here, and there's a lot of down going on, so we have that going on and that going on. So we're going to have a resultant, that's that right there, so that's going to be FB, and this is FB double prime, and this is F prime right here. So if we're going to try to figure out from horizontal, no, I don't like to measure from right there. I like to measure from here, right there, okay? From the, right there, so that's theta FB. We'll take the inverse tangent, and so the run of this, of F, is going to be FBX double prime, so it's going to be 2,000 again. And the rise of it across that angle is going to be that FB double prime Y. So that should be 4,000, right? Yep, 4,000. But it's going to be 4,000. But we're going to add in the 333.3 here. And what we end up finding is we have 65.22 degrees downwards, right there. And then lastly, we don't have much room here, so let's pull it down a little bit. We're going to have, let's take a look at him up above. And it's going to go up and to the left. Yeah, up and to the left is going to be the double prime. So we have a downwards F prime, and then up and to the left F C double prime. And so I think it's actually coming up there. I think I did a bad job of drawing that parallel right there. So and we're going to end up seeing what this guy right here, that's going to be the FC here, this angle right in there. So we go theta FC is going to be the run, let's see, inverse tangent. I think this is also a 2,000. 2,000 shows up a lot of the times. So for, actually it's up here, right? So the run is actually 4,000. Yeah, okay, so the run is 4,000. Yeah, is that true? Yeah, let me just double check on this. Yes, up here. Okay, so that's this one up above is a better drawn one there, so it's going to be the cosine. So it's the 4,000, and the rise is going to be the FC double prime Y. FC double prime Y is the sine of the thing. Yeah, so it's going to be 2,000. Minus the 333.3, so we end up with 22.62. And one of the reasons why I went ahead and did this problem was because a lot of them are symmetric and that kind of thing, and I wanted one that was not symmetric. So that's going to be all the directions if that was the thing that was going to be asked. It's more important, I think, is the what's the failure of this thing. So B is the largest force, so therefore the largest stress. So what we do for that guy is take tau and take our 4,773, and these are half-inch bolts, so pi over 4, 0.5 squared, and we get 24.31 KSI. And since they're grade 2 bolts, we look up and we find what the yield strength of them are, and that's in a table in the chapter, and we find that that's going to be 57 KSI, but that's normal stress. We need shear stress, so we take 0.577 times our SY, and we get 32.91 KSI. And what we're left with is a safety factor, shear yield divided by tau. This is apples to apples, 32.91 divided by 24.31, and we're left with 1.35. And so that's the answer to this example. I didn't ask for any of the other failure modes, but because of the arrangement, there's probably not many that are likely, but we could imagine that the bolt would shear through and tear through this part right here, and yeah, and maybe it would pivot about A because it doesn't have as much load. So, but the thing is that it would have to shear through this right here. Sometimes, there's not a practical way for for some of these failures to actually take place, because there might be something more stuff in the way, or there might be another support in here. But when you have when you don't have that many bolts, there's more of a chance of one of these types of failures of taking place. But if you had like 6 bolts in there, even though one somewhere near the edge, the chances are that it's not going to rip through the others. But it's best to be cautious and when designing the thing and not get too close to the edge. But sometimes arrangement makes it so. And so there you go. There's I could have just presented this stuff, and but I decided to write it out. And so I'll discard all this stuff and post a video.